In this lesson, we're going to solve systems of linear equations involving three variables, x, y, and z. Now, you will not be expected to graph these equations involving three variables, but if you were to graph them, we would need an x, y, and z axis. And when we graph an equation involving three variables, we end up with a plane. Now again, you will not be required to graph these problems, but it's helpful to see a visual representation of what these graphs and their solutions would look like. And we're going to look at two cases in this video. If we remember from my chapter 3.1 video, when we found the solution for a system of equations by graphing, the solution was the intersection point. So let's suppose we had a system of three equations involving three variables. And when we graphed those equations, we got three planes, like you see here. The solution is the point where all three of those planes intersect, which would be this point right here. So for this particular case, the number of solutions would be 1, since there is one point of intersection. The way we write our solution for systems of equations involving three variables is as an ordered triplet. And it's called an ordered triplet because it contains three coordinates, an x-coordinate, a y-coordinate, and a z-coordinate. For example, let's say that this intersection point was the ordered triplet 3, 4, -7, where 3 is the x-coordinate, 4 is the y-coordinate, and -7 is the z-coordinate. Our solution would be that ordered triplet, where all three planes intersect. Now, the next case that we're going to look at is this case that's shown here. When you're solving a system involving three equations, your solution is the point where all three of those equations intersect. For this picture here, we see that there is no point where all three planes intersect together. Here, only two of the planes intersect. Here, only two of the planes intersect. And here, only two of the planes intersect. Same with this diagram here. Here we have three different planes, but they are all parallel, so they never intersect. If you have a situation where all three of your planes never intersect together, the number of solutions will be none. And we can write our solution using any of these ways here. Here's an example of a system of three equations involving three variables, x, y, and z. Now, before we learn how to solve a system of equations like this, we're going to first discuss what it means for an ordered triplet to be a solution to a system of equations. In order for an ordered triplet like this to be a solution to a system of equations like this ordered triplet must create a true statement when it is plugged into this equation, and this equation. And with ordered triplets, the first number represents the x-coordinate, the second number represents the y-coordinate, and the third number represents the z-coordinate. And to help ourselves stay organized, I'm going to label these three equations, equation 1, 2, and 3. So let's start by plugging in this ordered triplet into equation 1. So I've plugged 3 in for x, 2 in for y, and -2 in for z into equation 1. If we simplify, 3 plus 2 gives us 5, and 5 plus a -2 gives us 3. So we end up with the true statement, 3 equals 3. Let's see if this ordered triplet also gives us a true statement when we plug it into equation 2. So we plugged in 3 for x, 2 for y, and -2 for z. Now I'm going to simplify to see if we get a true statement. We end up with the statement 15 is equal to -23. This is not a true statement. So we can stop here. We don't need to even bother plugging in this ordered triplet into equation 3, since we already see that this ordered triplet does not satisfy equation 2. So we can say that this ordered triplet, 3 to -2, is not a solution to this system of equations. Let's quickly check the ordered triplet given for example B. So in order for this ordered triplet to be a solution to this system of equations, it must create a true statement when plugged into all three equations. So I'm going to start by plugging in this ordered triplet into equation 1. And again, we'll plug -4 in for x, 1 for y, and 6 for z. We end up with the true statement 3 equals 3. So now let's go ahead and plug this ordered triplet into equation 2. And we get the true statement, -23 is equal to -23. So now let's go ahead and plug this ordered triplet into equation 3. And we get the true statement, 17 equals 17, when we plug this ordered triplet into equation 3. So since this ordered triplet gave us a true statement when we plugged it into all three equations in the system, that means that the ordered triplet -4, 1, 6 is a solution to this system of equations. Next, we're going to learn how to solve a system of equations involving three equations and three variables x, y, z. In chapter 3.1, we learned how to solve systems of equations involving two equations and two variables x and y. We solved these equations by graphing. The solution was the point of intersection. We also solved these equations using substitution, and we also solved these equations using elimination. All three of those methods work for solving systems of equations involving two equations and two variables. When we have systems of equations involving three equations and three variables, we don't solve them by graphing because it would be quite difficult to draw planes on a three-dimensional XYZ axes by hand. We could solve using substitution, but it's usually never done that way. The approach that is usually used, and the approach that we are going to learn and use, is elimination, because that is the most efficient and straightforward way to solve systems of equations involving three equations and three variables. And I've typed out the steps for solving systems of three equations using elimination, and we're going to follow each of those steps one by one next. First, I'm going to label our equations A, B, and C just to help stay organized. Now, for step 1, we can select any two of the equations and use the elimination method to eliminate one of the variables. So we have lots of flexibility with step 1. To start, we just need to pick any two equations. It doesn't matter which two you pick, so you could pick A and B, or A and C, or B and C. Any of those pairs will work. For step 1, I'm just going to randomly decide to pick equations A and B. Now we have to make another choice in step 1. We also have to decide which variable we're going to eliminate. We could eliminate x, y, or z. It doesn't matter. Any of those variables will work. So I'm going to randomly decide to eliminate x. So first I'm going to copy down equations A and B. Now, we are going to use the elimination method to eliminate our chosen variable, which is x in this case. In order to use elimination to eliminate the variable x, we need to get the coefficients of the x's to be matching but opposite. To accomplish that, we could multiply this top equation by -4, because then we would have -4x and +4x. So we want to multiply each and every term of this equation by -4. -4 times x will give us -4x. -4 times -2y will give us a +8y. -4 times 5z will give us a -20z. And -4 times -17 will give us a +68. And then let's go ahead and bring this bottom equation over. Now, we're on the right track because we decided that we were going to eliminate x in step 1. And in order to eliminate x, we need the coefficients of the x's to be matching but opposite. And that's the case here. We have -4x and +4x. So, when we learned the elimination method in section 3.1, we learned that once one of your variables has matching but opposite coefficients, the next step of the elimination method is to add your equations together. So let's see, when we take negative 4x plus 4x, those cancel to give us 0. 8y plus negative 3y will give us 5y. Negative 20z plus z will give us a negative 19z. And 68 plus negative 10 will give us 58. We've successfully eliminated x here. I'm going to box this answer and I'm going to highlight it because we're going to come back to this answer in step 3. Now let's move on to step 2. In step 2, we want to select any two other equations and use the elimination method to eliminate the same variable from step 1. So in step 1, we picked equations A and B. In step 2, we want to pick any two other equations. We could either pick the pair A and C, or we could pick the pair B and C. Either of those pairs will work. I'm going to just randomly pick equations B and C. Now, in step 1, we could decide to eliminate any variable. We could have eliminated x, y, or z in step 1. It doesn't matter. But in step 2, you have to eliminate the same variable that you did in step 1. So since in step 1 we eliminated x, in step 2 we have to eliminate x again. If we eliminated y in step 1, then we would eliminate y in step 2. If we eliminated z in step 1, then we would eliminate z in step 2. So I'm going to start by copying down equations B and C. And to eliminate x, we need the x's to have matching but opposite coefficients. So to accomplish that, let's multiply this bottom equation by negative 2, because then we would have positive 4x and negative 4x. I'm going to start by copying this top equation over here. Now let's multiply all terms in this bottom equation by negative 2. Negative 2 times 2x will give us negative 4x. Negative 2 times y will give us negative 2y. Negative 2 times 3z will give us negative 6z, and negative 2 times 0 will give us 0. Now we can see that we're on the right track because we wanted to eliminate x, and we've got the x's to have matching but opposite coefficients. Now let's go ahead and add these two equations together to eliminate these x's. These x's will cancel to give us 0. Negative 3y plus negative 2y will give us negative 5y. Z plus negative 6z will give us negative 5z, and negative 10 plus 0 will give us negative 10. And I went ahead and boxed and highlighted this because we're going to need this equation in step 3. Notice that we now have two equations, and both of those equations involve the same two variables, y and z. In step 3, we're going to use the elimination method to solve the two equations that resulted from steps 1 and 2. So in step 3, we're going to solve these two green equations using elimination. So first I'm just going to copy down these green equations here and here. Now we have a system of two equations involving two variables. In chapter 3.1, we had lots of practice solving systems of two equations involving two variables using elimination. To solve a system like this, we need to either get the y's to have matching but opposite coefficients, so that the y's will be eliminated, or we need to get the z's to have matching but opposite coefficients so that the z's will be eliminated. Either approach will work, but I noticed that the y's already have matching but opposite coefficients, so it's going to be easiest to eliminate the y's. And since the y's already have matching but opposite coefficients, the next step of the elimination method is to add these two equations together. So 5y plus negative 5y will give us 0. The y's will cancel. Negative 19z plus negative 5z will give us negative 24z. And 58 plus negative 10 will give us 48. Now, we've almost solved for z. To isolate or solve for z, let's divide both sides by negative 24. And that will leave us with z is equal to negative 2. Now, we've found one variable, but when you're solving a system involving three variables, we need to make sure to find all three variables. So now that we've found z, we can plug z into either of these two equations to find y. Now at this point, make sure you do not plug z into one of the original equations because you'll find that you'll get stuck and that will not help you to find one of the other variables. So make sure to plug z into either of these two equations. Doesn't matter which you choose, they'll both give you the same answer. I just picked this top equation right here, and I've plugged -2 in for z. If we simplify, this will leave us with 5y plus 38 is equal to 58. Then let's subtract 38 from both sides. And that will leave us with 5y is equal to 20. Then we can divide both sides by 5. And that will leave us with y is equal to 4. Now we found two variables, y and z. The last step is we have to find the third variable, x. To find x, we want to plug these two variables into any one of the three original equations. I'm going to plug y and z into equation A. So I plugged 4 in for y and -2 in for z into the original equation A. Now let's simplify. And once we simplify, we find that x is equal to 1. So we've found our three variables, x, y, and z, and we'll write our final answer as an ordered triplet. And for our ordered triplet, we put the x coordinate first, then we put the y coordinate second, and we put the z coordinate third. Now, you can always check your answer. Since this ordered triplet is a solution to this system of equations, that means that this ordered triplet creates a true statement when it's plugged into all three of the equations. So you could take this ordered triplet, plug in 1 for x, 4 for y, and -2 for z into this first equation, and make sure you get -17. Then plug that ordered triplet into the second equation, make sure you get -10, and plug that ordered triplet into this third equation, and make sure you get 0. Let's take a look at another example. I'll start by labeling the equations A, B, and C just to help us stay organized. Now, for step 1, we need to pick any two equations and we can eliminate any variable, x, y, or z. There are several different options here, and the two equations and the variable that I pick might be different from the two equations and the variable that you pick for step 1, but that's okay. We can both end up with the same correct answer in the end. While we have lots of different possible options that will work for step 1, we could make a wise decision here that will make our work in step 1 a little bit quicker and easier. So in step 1, we pick two equations, and then we eliminate one of the variables. Now, in order to eliminate a variable, that variable must have matching but opposite coefficients in the two equations that you choose. So let's take a look here. Do any pair of equations here have a variable with matching but opposite coefficients? Yes. In fact, if we look at equation A and equation C, the y's have matching but opposite coefficients. We have -2y and +2y. So it will be really quick and easy to eliminate y in equations A and C. So I'm going to decide to pick equations A and C and eliminate y for step 1. I'll start by copying down equations A and C over here. Now, like we said, the y's already have matching but opposite coefficients. So we can proceed to add these two equations together and our y's will be eliminated. Let's see. 2x plus -5x will give us -3x. -2y plus 2y will give us 0, so the y's will be eliminated. 1z plus 1z will give us a +2z. And -10 plus 9 will give us -1. Then I made sure to box and highlight our answer here because we will use this answer in step 3. Now in step 1, we picked equations A and C. In step 2, we want to pick a different pair of equations. So we could either pick equations A and B, or we could pick equations B and C. Either pair of equations will work. I'm going to randomly decide to pick equations A and B for step 2. Now, remember, whatever variable you eliminated in step 1, we have to eliminate that exact same variable in step 2. So since we eliminated y in step 1, we need to eliminate y again in step 2. So I'm going to start by copying down equations A and B right here. Now, since we need to eliminate y, we need to make it so that the y's have matching but opposite coefficients. To do that, we could multiply this bottom equation by 2, because then we would have negative 2y in the top equation and positive 2y in the bottom equation. So I'm going to start by carrying this top equation over here, and then let's multiply each term in this equation by 2. 2 times 3x will give us 6x, 2 times y will give us a positive 2y, 2 times negative 2z will give us negative 4z, and 2 times 4 will give us 8. Now, we are on the right track because we wanted to eliminate y in step 2, and we see here that the y's have matching but opposite coefficients. So when we add these two equations together, the y's will be eliminated. So let's go ahead and add these two equations together. 2x plus 6x will give us 8x. Negative 2y plus 2y will give us 0. The y's will be eliminated. 1z plus negative 4z will give us negative 3z. And negative 10 plus 8 will give us negative 2. And I went ahead and boxed and highlighted this answer here because we're going to use this answer in step 3. Now for step 3, we're going to solve the two green equations above using elimination. So I'm going to start by copying down these two green equations right here. To solve a problem like this using elimination, we need to either get the x's to have matching but opposite coefficients, or we need the z's to have matching but opposite coefficients. Let's suppose we want the x's to have matching but opposite coefficients. One approach we could use is we could multiply this top equation by the coefficient of this bottom x, 8. And then we could multiply this bottom equation by the coefficient of this top x. And even though this is a negative 3, when I'm deciding what numbers to multiply in pink here, I always like to start with positive numbers. So I'm going to start with a positive 3, and then I can switch one of the numbers to negative if I need to. Let's see. 8 times negative 3x will give us negative 24x, and 3 times 8x will give us positive 24x. So it looks like we'll end up with the x's having matching but opposite coefficients. So let's multiply each term in this top equation by 8. 8 times negative 3x will give us negative 24x. 8 times 2z will give us a positive 16z. And 8 times negative 1 will give us negative 8. Then let's multiply each term in this bottom equation by 3. 3 times 8x will give us 24x. 3 times negative 3z will give us negative 9z. And 3 times negative 2 will give us negative 6. Now it looks like we're on the right track because we decided that we were going to eliminate the x's here. And we've succeeded in getting the x's to have matching but opposite coefficients. So when we add our equations together, the x's will cancel. 16z plus negative 9z will give us 7z. And negative 8 plus negative 6 will give us negative 14. Now we've almost found z. To find z, we just need to divide both sides by 7. And that will leave us with z is equal to negative 2. So we've found one variable, z. Now to finish step 3, let's find the other variable, x. And remember, to find the other variable, do not plug z into one of the original equations. You'll get stuck at this point, and it won't help you to find another variable. Instead, we're going to plug z into either of the two green equations to find x. Either green equation will work. I'm just going to pick the top green equation. And I'm going to plug negative 2 in for z. And then I'll proceed to solve for x. Now we found two variables, x and z. For step 4, to find the last variable, we're going to plug x and z into any one of the three original equations. I'm going to pick equation A, and let's go ahead and plug in -1 for x and -2 for z, and then let's proceed to solve this equation for y. So we found our three variables, x, y, and z. Now let's write our final answer in the form of an ordered triplet. We start with our x coordinate, which is -1, then we list our y coordinate, which is 3, and then we list our z coordinate, which is -2. Let's take a look at one last example together, and we'll see that we're going to get a different type of solution for this problem. Step 1, we want to pick any two equations and eliminate any variable, x, y, or z. But remember, in step 1, we can often make our work a little bit easier by making a wise decision. When we're deciding what variable to eliminate, it's always easiest to eliminate a variable when that variable has matching but opposite coefficients in your two equations. There are a few different options here. Notice the y's in equations A and B have matching but opposite coefficients, -1y and +1y. Another option, notice the z's in equations B and C have matching but opposite coefficients, -3z and +3z. So either eliminating the y's in equations A and B or eliminating the z's in equations B and C would be the easiest way to approach step 1. So I've decided to pick equations B and C and to eliminate the variable z. I'm going to start by copying down equations B and C right here. Now, because the variable z already has matching but opposite coefficients here, we can add these two equations together and the z's will be eliminated. So if we add -2x plus 1x, that will give us -1x or -x. 1y plus -2y will give us -1y or -y. The z's will be eliminated, and 5 plus 2 will give us 7. For step 2, we want to pick a different pair of equations. I'm going to pick equations A and B, and we want to eliminate the same variable that we eliminated in step 1. So we eliminated z in step 1, so we'll eliminate z again in step 2. So I'm going to go ahead and copy down equations A and B right here. Now we want to eliminate z. So that means we have to make it so that the z's have matching but opposite coefficients. One approach we could take is we could multiply this top equation by the coefficient of this z. And even though this is a -3, I'm going to start out with a +3. And then we can multiply this bottom equation by the coefficient of the top z, which is 2. And let's see if this will work out. 3 times 2z will give us 6z, and 2 times -3z will give us -6z. So this will make it so that the z's have matching but opposite coefficients. I'm going to go ahead and multiply each term in this top equation by 3, and then I'm going to multiply each term in this bottom equation by 2. Now it looks like we're on the right track because we wanted to eliminate the z's, and we've made it so that the z's have matching but opposite coefficients. So now let's add our equations together. 3x plus -4x will give us -1x or -x. -3y plus 2y will give us a -1y or -y. The z's will be eliminated. And -21 plus 10 will give us -11. Now, in step 3, we're going to solve these two green equations using elimination. I'll start by copying down these two green equations right here. Now, in order to solve these two equations using elimination, we need to make it so that the x's have matching but opposite coefficients, or the y's have matching but opposite coefficients. Either will work. Let's suppose that we want the x's to have matching but opposite coefficients. Well, right now we have -1x and -1x. So the coefficients match. To make the coefficients opposite, let's just multiply one of these equations by -1. I went ahead and multiplied the top equation by -1. Let's multiply each term in this top equation by -1, and then let's carry over this bottom equation. Now, I had intended for the x's to have matching but opposite coefficients, and they do. We have 1x and -1x, but it just so happens that the y's also have matching but opposite coefficients. We have 1y and -1y. So let's see what happens when we add these two equations together. X plus -x gives us 0, so the x's are eliminated. Y plus -y also gives us 0, so the y's are also eliminated. So we're left with nothing, or 0, on the left side of the equation. And then -7 plus -11 will give us -18. So we end up with the false statement, 0 equals -18. Remember, in math, if you're solving a system of equations and you end up with a false statement, that means that there is no solution. So we can write our final answer like this, or we could write our final answer using any of these different ways. So if you were to graph these three equations on a set of x, y, z axes, there would be no place where all three of these equations intersect in the same spot.